Hi, Jay, can you hear me?
Hello. Yeah, I can hear you.
Okay. Yeah, sorry. My previous meeting ran late. Couldn't finish it on time. Okay, so before we start today's class, I just wanted to ask some logistical questions since we are approaching end of term. Um, for your other courses, are you guys having exams in December or in January? Jay?
Actually, I've just been attending this and the Kedar reading course because I talked to Weber when the group theory courses. I don't really need to do that, but I don't think any date has been announced for that. I'll still continue to do it, but I
So
don't think.
you are just attending the group theory course as an audit course. You were able to get it changed formally?
No, but he said that it won't really show up in your transcript if things go bad. That's what he said. I mean, he said that it doesn't need. There's no requirement to change it formally, but you can treat it like that. So I said, okay.
Oh, okay. I mean, normally there is, because if it is a course, then there has to be a grade against it. Anyway, what about Srijita?
We had midsems, but exams are supposed to be in January, I think, after everyone comes to TIFR.
Who's everyone?
Everyone meaning the new batch students who are supposed to join, they are supposed to come in January. So after once they come, then the teachers are supposed to take the exams.
The new batch students won't be taking classes with you, right?
Yeah, they are. I mean the PhD ones they are taking.
Oh, acha, PhD one,
Yeah.
because, but wait, you are third year integrated PhD, right?
Yes.
So which courses of yours are being taken by first year PhD students?
Atomic and molecular, and astrophysics I don't think so, but atomic molecular there are people.
And the reason for them to come back is what, you're going to actually have a in-person examination.
He didn't say anything of this sort, but I don't know if it's going to be offline or online. But according to SBP, it's supposed to be conducted once everyone is there in the institute in person, has joined formally. Yeah.
Okay, that's kind of strange because SBB mean this you heard from Weber.
No, the teachers themselves had said
Oh, the teachers.
yeah,
Okay,
yeah.
I'll then need to double check this because I checked with Weber, he said the date for submitting the final grades is January 10th. And all the first year students are not all going to show up on a single day. It's still going to happen in the same way like it has been for
Yeah.
the past few months. They're going to come in like in batches, but
Mm.
it's going to be faster because we are now, the quarantine period has been reduced and all of that stuff, but they're not going to all show up
At once.
on day one. So
Yeah.
so conducting exams after everybody comes is, now there is been some priority given to like students in experimental departments versus theory departments, but still it would, I don't imagine that it's going to happen before January 10th. Okay, but any other, I mean, Srijita, how many, I guess you also probably not taking that many courses, right?
I'm taking 2 courses apart from this.
Atmol, and what that was, you taking the astronomy?
Astrophysics, yeah.
Okay, that, does that have a final exam?
Yeah.
Okay.
Again, probably at the end of January.
End of January. Okay.
Yeah.
Okay, so then I guess maybe I should just check with Vaibhav again on what's going on. So I was basically wanted to know that information so that we can plan sort of our end of course and when we have to do the the circuit design and all of that stuff, because it's running a little bit short on time. But in terms of the lectures or for the other courses, are you guys all close to finishing up or it's still going on?
Still going on.
Yeah, I mean, it's not probably at the midway mark or a little bit ahead of that, but not really towards the, at least in the group theory course. That's
Midway. Okay, I would have thought that the lectures were supposed to end by the end of this month, at least. Okay. Have the other classes also been somewhat irregular?
Yeah, sort of. I mean, we have missed a reasonable number of group theory classes.
Okay, who's taking group theory?
Gautam.
Okay. Okay. Okay, I guess then things are all a bit up in the air. So I will speak with Vaibhav, and then maybe by next week I will have like a plan for the rest. So anyway, as I mentioned last week, that we will now do 3 lectures a week for the rest of the month, and I think that basically would cover in terms of what formal things I wanted to sort of cover as a course. And then next week we will start planning about the projects. Basically, once I finish discussing the scattering matrix formalism, which will be the next 2 lectures after today's, then we can start thinking about the actual components, and then basically we'll assign each one of you a different microwave component to study about, design it, simulate it, and then get it fabricated and tested. So that's hopefully we can finish that up by first week of January. If there's more time, then we can push it a little bit more. Okay, so let me. Oops. Opening up Microwave Office. Okay, so last time we discussed more about resonators, and then we looked at the resonators in transmission. Talked about the differences in the response of the transmitted signal and the reflected signal if one looked at a transmission resonator in reflection. And then we ended with looking at the asymmetric resonator, where it effectively is really damped by one end, but there's a second weakly coupled port used to just excite, and what happens to the transmission signal in that case. Okay, so there was, and then we sort of ended with this notion that such a resonator in transmission behaves sort of like a filter, and that's one of the applications of such devices one could do. So we will talk about some aspects of filters today. There is a lot of detail there in POSAR, which I will email you after today's lecture, and you can read up and we can discuss that in a slightly different format, where basically you read it up, try to implement some of those ideas in Microwave Office, and then during a class you will ask me questions based on what you have done. So for example, you can share your screens and then we can try to figure out what's going on. So there was just one other small thing I wanted to add to our discussion of last time. So, okay, this is still back in symmetric form. And okay, I guess I had introduced this output equations and how to compute these quantities. But just to go back to just the regular transmission properties of such a resonator, I've kept the simple case of the symmetric case. Okay. So this was the transmitted amplitude. I just wanted to point out one more thing, which is related to the transmitted phase. And so let's set that up. So this is something useful to remember, that the transmitted phase for a symmetric resonator like this, in fact, I think it works for asymmetrics as well, but we'll just check with, again, no loss and things like that, looks very similar to the phase response of the reflected resonator, like the single port reflection resonator, with one difference. Wait a second, something is not right here. I guess there's a little bit of overall phase offset, which is why it was looking a little strange. Let me fix this. I just want to get the divisions to show up properly so that it makes sense. Why 0 is not showing up? All right, okay, now we can at least see the 0. But actually, as I realized, 0 is also not very useful. So in the ideal case, the difference between the phase response, in fact, it has a very similar shape. And I think if you analytically work out, I think it will have a very similar form as well. Instead of going from plus 180 degrees to minus 180 degrees, in transmission, it actually, if this was symmetric, so remember that you see that this is not symmetric in about 0. The resonant frequency is actually here somewhere, which is obvious from this one. Maybe I should move this guy to the other one now. So see, the resonant frequency is somewhere at 9.121, which is like somewhere here. Okay, that's the symmetric point about these two extremes, and not at 0. This is again because of the presence of your these coupling capacitors, which sort of add an additional phase to the overall situation. Just like you saw in the reflection case, that when you had coupling capacitors, you have this, instead of something which looks like this, you had something which looked like that, just an overall phase shift down here. So similarly here also, there's a slight downward phase shift. But if you look at the extremities, so this is now going towards about plus 70 degrees, and this one is going about minus 100. So close to 180 degrees is the total uh, extent of the thing. So maybe we can actually look at it. Excuse me. A larger range here. So you see here, it's sort of now 77 and 110. So about 180 degrees or so. So that's the difference you have to, but otherwise everything else looks the same. And this is just useful to know, just as a property of looking at phase shifts in transmission. Later on, when I discuss this in the context of qubit measurements, that actually is sort of slightly more of quantum measurement related things, but it's, since these are all being used for that, it's useful to discuss that. You will see how this fact that, the overall phase shift is roughly half the value of the reflected case, what kind of implications it has. Let's go back to previous range. And then one other useful thing to know is that if you looked at in dB, then the 3 dB points, which is basically when the power drops by a factor of 2, give you the bandwidth of the resonator. So let's just maybe even zoom in a little bit more. 8.5. So this of course is the top of the curve is 0 dB because it's power ratio of 1, and then you come to 3 dB. So let's add a marker here. Put it at approximately 3 dB. So 8.99 to 9.257. This is now the delta omega, which defines the Q factor or the bandwidth. And I don't remember exactly now, but we can just verify this, that if we now go to the real part and compare if the same argument we used for the reflected signal, which was related to the full width half max of the real part, whether that works or not. So if we, there's something strange going on here. What is this? It's like
In dB, this is like the square of the magnitude. that we're plotting?
That's right. It's the square of the magnitude, but in logarithmic units.
Okay, which is why we're now looking for the by 2.
That's right. Yeah. Yeah. We're looking for the by 2 points. But there seems to be something strange going on here, unless I'm misremembering this, because the transmitted case with coupling capacitors makes things somewhat complicated. That the peak of the real part doesn't even seem to coincide with the peak of the log magnitude. Okay, maybe I'll need to come back to this. Maybe the real part is not very useful for looking at transmission. And the thing is, we look at reflected signals only for almost 99% of the things that I don't remember what was the situation. But the transmitted phase being roughly half is correct. And in fact, it's a little bit more what is really correct is how the phase changes at resonance, like the delta phase for a given change in basically what I mean is the slope of the phase curve here is exactly half of the reflected case. And that is what has implications for quantum measurements, which we'll discuss later on. Okay, anyway, so we will finish up here with this last point about looking at the 3 dB things. But I will just double check this and send you a message on whether the real part and imaginary parts are useful to look at. But why don't we look at the imaginary part just to see how it looks like? Yeah, it has a similar kind of shape, but okay. Right, just 1 second. So again, this curve highlights the possibility of using these kind of systems as filters comes about. And again, those 3 dB points are useful to know because typically the bandwidth of filters is often defined with respect to 3 dB. When you say that a certain filter has this much bandwidth, usually, not always, sometimes they make it explicit. They'll say a 3 dB bandwidth of so-and-so. And just as an aside, these kind of numbers have implications when one is computing, integrated power in a certain range of frequencies. And there are some physics calculations where this can actually make a difference because one needs to know how much bandwidth to use, especially when you're computing things like spectral density and things like that, where it's basically power in a unit bandwidth. So then whether it's a 3 dB bandwidth or a 10 dB bandwidth, there are actually various conventions for defining those things. We are not going to be discussing that in this context, but I just wanted to mention it. Sometimes, in fact, we have noticed that some commercial filters even give you a 1 dB point as the relevant bandwidth. And then if you look in the data sheet, it will have more details that, okay, 1 dB is this much, 3 dB is this much, and so on and so forth. So the moment you talk about filters, and of course you want the ideal filter to have perfect transmission at the frequency it's defined. And this type of filter, which has a transmitted band, somewhere at a finite frequency, these are called band pass filters. Okay, They're not necessarily the most common type of filters. There's something called low pass and high pass as well, which allow, low pass allows all frequencies below a certain frequency to pass, and high pass allows all frequencies above a certain frequency to pass. And at least Jay and Srijita, if you remember the discussion we had about filters and their non-idealities, that these definitions don't apply to arbitrarily high frequencies because the properties are not defined at arbitrarily high frequencies. So if there's a 10 gigahertz low pass filter, which is supposed to pass everything below 10 gigahertz and nothing above 10 gigahertz, with some roll off, it doesn't mean that it works at 50 gigahertz as well. It could be perfectly transmitting at 50 gigahertz. So that's just something to keep in mind in terms of practicality of when using real filters. And this is because the components which make up those devices often don't work at those high frequencies. Again, depends on exactly the kind of construction one is talking about. Now, if one is talking about a system like this, now this is of course more complicated. We can say, okay, this is a band pass filter which works here, but we all know what happens to this if I now extend the range of this simulation over a much broader range of frequencies. Here's a second transmission peak, right? So to call it a bandpass filter and expect that this actually is the only range of frequencies here, which is transmitting, is a misleading thing. So any of these filters which are made using sections of transmission lines, they typically have some periodicity in their response. And so this is at 9, this is at 18, right? It's roughly twice the frequency. As you would expect, the next standing wave would come up with 2 half wavelengths fitting into the length of the transmission line. So
Are the numbers on the left, are there just something which is remaining from the previous graph?
Yeah, this is just the, sorry, these are all the things got messed up. Let me put this back on the left thing and yeah, that was just the other axis there.
Okay.
Even though I removed the measurement, it somehow didn't get rid of it. But I'm guessing one cannot just have a right axis. Maybe that's the reason. Okay, so now, Jay, since we are talking here, there's a clear difference between this first peak and the second peak. What is it, and why do you think it is like that?
Bandwidth is certainly higher for the second peak.
Yes, and why is that?
I think how many wavelengths you can fit in, at higher modes, that is less sensitive to changes in frequency. That's how I would imagine it. When you're talking about something like a 180-degree phase, adding a bit more phase or removing some phase is a higher percentage difference.
That's an interesting argument, but it's not. Remember, if that 180 degrees was the only mode which was present, then that would have still made some sense. But the next mode is going to be exactly the same distance away, right? So this distance is roughly 9 gigahertz, and the next one is also going to be roughly 9 gigahertz. So let's take a look. Right. So the relative changes with respect to the fact that you're saying that overall number is now much higher, many more wavelengths are there, so it has less of a dependence. That's not really what's going on here. Let's see, Srijita, any ideas?
No.
What sets the forget the higher modes, even for the lowest mode, what decides this bandwidth in the current structure? Like if I wanted to change the bandwidth of say the lowest mode, what will I change in my circuit to change it?
The values of C.
These values, right?
Yeah.
Right. That is correct. So now, can you tell me what might be going on? What is the role of those capacitors?
They are supposed to help in reflecting the wave, and then we get this interference. So
Yes. And so keeping that idea in mind, when does the bandwidth lower or higher depending on that role it's performing?
bandwidth will affect the quality factor.
No, those are the same things. Right? Bandwidth and quality factors are just two ways of saying the
Yeah.
same quantity. So what I'm saying is that what aspect of that, so you're right, the capacitors are basically playing the role of reflectors, right? They are basically the mirrors, right? In the equivalent of the mirrors in the case.
Yeah.
So when does the bandwidth, when is the bandwidth very low, or the resonance very sharp?
The impedance of the capacitors depends on the
Yeah.
Exactly.
Oh yes, yes.
The
Because
transparency of the
impedance
mirrors
of the capacitor will
is
change
not the
with
same, right? It's the same capacitor, but 1 over omega c, which is the impedance, is going down as we go to higher frequencies. So because of that, the mirrors are a lot more transparent at higher frequencies than they are at lower frequencies. So it's a lot more open and connected to the environment at the higher frequencies for the same value of the capacitance. And that's why the resonance becomes broader as you go to higher and higher frequencies. The same thing would be opposite if we had used, say, an inductor in series as the mirror. Of course, you would need a very large inductor to make it work. But then in that case, the inductor would become more and more less and less transparent at higher frequencies, and the resonances will become actually sharper if you go higher. Okay. So the two things to remember, that the transparency of the capacitor matters. The capacitor's transparency is not frequency independent, so that will cause the different modes to have different bandwidths. And in fact, this has a sort of a practical problem in real experiments. Normally, you're interested in the lowest mode only, but these modes do exist. And because they are a lot more strongly coupled to the environment, they can have some unwanted behavior, that maybe they don't, they're having too much noise. And then if the physics, and it often happens that your qubit, which is coupled to your cavity, could also be coupled to these higher modes, depending on some details, then you can have problems. So controlling these higher modes can sometimes be a tricky issue. Okay, so filters using such sections of transmission line always are going to have some kind of a periodic behavior. And if this is not acceptable, then you have to do something different for constructing your filter. Now, you could, of course, construct a filter using a parallel LC circuit like this. And again, it would depend on the frequency at which you want to operate. That would determine whether capacitors and inductors can indeed be made in a realistic fashion. But for now, if we assume that that is possible, this can also be turned into a transmission geometry in a very simple fashion. And let's put the coupling capacitors as well here. So this is sort of the equivalent circuit of a of the transmission line version near one frequency, because this circuit only has one resonant frequency which is set by the L and the C, whereas this circuit has many resonances. So if one had to make a equivalent model of that, one has to somehow cleverly combine um, several such oscillators, each one of them at a different frequency as determined by this plot. So there are ways to compute that effective capacitor model as well, depending on which, effective LC model, depending on which mode you're looking at. And they will have different ratios of inductors and capacitors showing up. Okay. And there's actually, I think, a nice discussion. It's there in POSA, so you can look at it, but there's also a thesis chapter which actually discusses all the circuit QED things by Dave Schuster. I think it has a very nice discussion as well. So I'll find those relevant pages and send you a link for that. Just hold on a second. Yeah. Okay, so if we now go back to this guy here, now CC is not defined. Okay, and okay, I guess they had designed this in this global in here. Let's make it somewhat similar to what we had. Right. Oh, this is the impedance, not the. Okay, compute that. Let's see if R. -9 and -12 is 21.
I think there's a bracket missing at the end.
Ah. It's making it 15 gigahertz. Something like. That's good enough. 9.6. So I'll add again two-port transmission in dB. This one. And you see this has a very different response as you would expect. It's only one single pole. It's not reaching its maximum because of resolution issues. So let's make the coupling capacitor a little bit higher. So you can see that the coupling capacitor use is the same, but the Q factor is very different. And that's because the effective models L and C we have used here is very different from the what we have gotten from the transmission line. Okay, so it's just now it's a little broader, so it's going closer to the yeah. Okay. And you also see that even for something like this fall off is not as sharp as what happens on this side, right? It's not sort of symmetric, and that's actually a property of the LC oscillator. It's not supposed to be symmetric. The reason I'm sort of mentioning this is that quite often when we consider such LC oscillators as a single mode oscillator in physics problems, and in fact we will be doing that at least in our research in many contexts, we consider that to be a symmetric function because we actually are only interested in something very close to the resonant frequency. And right near the resonant frequency, the function is indeed symmetric. And in fact, we often do something called a rotating wave approximation, which comes up in many different contexts, but effectively for resonators, this is what it means. It actually changes the functional form of this resonator to a Lorentzian, which is symmetric. And that actually does not correspond to any physical device in reality. As long as you're only considering frequencies very close to the resonant frequency, it's fine. But that approximation is very useful because it makes many calculations easy and you can look at it. But this is sort of just a practical side point one has to keep in mind, especially if one is working with low Q oscillators, which we do in our research from the perspective of these so-called parametric amplifiers. Some of these approximations start to fail a little bit. Okay, so it's important to remember that depending on how the filter is constructed, or in this case, the resonator type filter is constructed, its frequency response could be asymmetric. It could have several recurrent peaks. The bandwidths of these could be changed. And also the fall off need not be as fast as you would like. So these are all important things to keep to mind. And there are ways to change this. One thing, of course, is that in practice, one would never make a filter like this if one really wants clean, very high frequency performances, because invariably at some frequency here, there will be spurious modes which will come up because these inductors and capacitors are not point-like objects. And the whole approximation of them being a lumped object is never really correct at high frequencies. Okay. So usually filters which are meant for operating at high frequencies are not designed using lumped element components. They're always designed using some kind of a transmission line section, but then that has its own caveats that there will be other modes, but depending on the design, one can actually suppress them or make them different. So we will see some other examples of filtered designs, and I think one of them I'll even do today. But the rest we will look at it from, as I said, in sort of this reverse class mode where you read up. But there's a lot of details on designing filters which are not often very used on a day-to-day basis. It's just useful to know that these ideas exist, because essentially all of the content in Posar, many of the things in content in Posar is is sort of old school, where you had to keep these tricks in mind. There were these rules of thumb and all. They're useful to keep in mind, but because of advent of very powerful computers and softwares, most of the designing is now done with just simulation. So you don't really need to remember any of these things. but it's useful to just go through them once and sort of keep them in mind. Okay, so for the next 10-15 minutes or so, I want to discuss something which is related to filters, but slightly connected to qubit stuff. And it also allows us to learn something about the software, how to measure. It's not very something new. We've seen it before. And this is basically related to the most common structure we utilize in our research, which is the qubit coupled to a cavity. Okay, and how does one analyze such a system in terms of its relevant properties? So we will look at that. So for that, I'm going to, I guess I'll start with this simple LC structure only. So I'm going to duplicate this.
I had one question. So what is the rotating wave approximation, like relation with rotating wave approximation you mentioned here?
Yeah, just 1 second, I'll see. So the rotating wave approximation, one way of, as I said, it actually comes in many different forms in physics, depending on how, what you're doing. But when analyzing resonators and their frequency response, and especially when you're writing down their quantum mechanical versions of the Hamiltonian and things like that, there is an implicit assumption you actually make. And the function you use is actually symmetric about the resonant frequency. Whereas you can see from even the LC model that this is actually not a symmetric function, right? So there is actually a approximation which is related to this term. Quite often you will get a term of this type. So omega resonance square minus omega square. So whenever you're analyzing any resonant circuits, you will get terms which will have this kind of a thing there, 1 over, and this will blow up. Usually if there's no damping, this term will blow up, but there is normally some other I omega gamma here or something like that. I'm forgetting the exact thing, but the essence of the rotating wave approximation in terms of the mathematical approximation you do is to note that because we are interested in omega close to omega naught. Basically what we are saying is that since this is a resonant circuit, I am only interested in the physics of the problem near the resonant frequency. Very far away from the resonant frequency, I don't care. Okay? Now when you have this approximation, you can rewrite this term as omega naught plus omega into omega naught minus omega. And then you approximate this guy and you say this is just 2 omega naught. Because this number are, both, first of all, omega is large and omega naught and omega are close to each other. So I'm just going to assume that this is not going to play a dominant role in defining the effect of this term. It's actually the difference term which is going to play the dominant role. Okay. So when you make this approximation, and then quite often you will move into a frame which is with respect to the omega naught. So then this will just become some other delta omega or something like that. So doing this approximation changes the large frequency response. But of course, it's sort of nonsensical because this is an approximation for frequencies only close to the resonant frequency. And this essentially the rotating wave approximation when you are talking about analyzing these kind of resonance circuits, is effectively doing this. And this simplifies the problem. It actually changes the number of poles you have in the complex domain if you want to sort of get into the details of that. And so it's actually not the same response function, but for small frequencies around omega, this is a perfectly good approximation, and that's what one uses. So see, this has lots of implications on certain quantities you compute. In fact, the part I'm going to discuss here is related to that. And there are certain formulas you would write down which are a direct consequence of this approximation, but you sort of tend to forget it and you keep using it even for larger frequencies, and then you get a wrong result. Okay, and you will actually see one of those things right now. So that's what, but the thing is, you might not even realize that this is what you're doing when you're doing rotating wave approximation in many, many different scenarios, because it's only when you look at resonance circuits like this that this becomes obvious. But essentially the same idea. You know, it's because there are these high frequency, very fastly changing terms here and very slowly changing terms here. If you go into a rotating frame, then these additional terms give you the very fast oscillatory terms which you throw away. And it is the slow term which is basically related to the difference between omega naught and omega, because it's now a small frequency. Those are the terms which contribute. So that approximation shows up in many different languages and many different forms. But for these kind of devices, it's essentially amounts to making this particular approximation in the calculation.
Okay.
So you'll see what I mean by this in this this example I'm going to discuss now.
Okay.
Okay. So the this basic element of any sort of basic qubit circuit in superconducting devices is a readout cavity, which is shown here as a LC oscillator. You know, it has some L and C, it is coupled to the environment, so that sets the bandwidth or something. And then this thing, now how exactly this readout cavity is made, again, is details. It could be a transmission line resonator, it could be a lumped element resonator, it could be a 3D cavity. All of those are details, and I'll mention what that entails. But we can always approximate all of them with a LC circuit of some appropriate LNC, again near the frequencies of resonance. That is again the approximation we're doing. But for now, let's assume this is the model. And then this is coupled to the transmon qubit, right, which is a Josephson junction and some capacitor. But for the purposes of this discussion, we actually don't care about the nonlinearity of this circuit. Because we are only interested in something related to the dissipation experienced by this qubit, and that's the thing we are going to look at. So since we are not talking about exciting to higher levels and things like that, I'm going to approximate this for the purposes of this calculation just by removing, basically getting rid of this Josephson junction, and then just replacing it with an inductor which has the inductance of that particular Josephson junction. I mean, for those who want to know, just for that value Lj is given by flux quantum divided by 2 pi into I naught, where I naught is the critical current of the Josephson junction. So this is the linear inductance of the Josephson junction, so that it has the same resonant frequency. You choose Lj of the right type, and then whatever the Cj you had. Okay. So let me now actually draw this here. Let's go use this. I'm going to call this C resonator qubit. This is Lj. This is Cj. Let me put values for that. Lj is usually around 10 nanohenries. Cj is about 80 femtofarads. These are typical numbers. I'm going to fix the value of these guys to be closer to typical values one has. something around 7 gigahertz. This is good. 7.121 and 5.6. Okay, excellent. So I just wanted to put typical numbers we typically use. So the qubit frequency is usually lower than the cavity frequency by about 1 or 2 gigahertz. So we have 5.6 and we have 7.1 for the cavity frequency. Okay. Now, if you, for some reason, thinks there is already a variable like that. Maybe it's because of this. Don't really know a good value for this, but this should be fine for this purpose. Okay, right. Now, the CC will determine the bandwidth of the linear resonator, as always, and the CRQ will determine how strongly the qubit is coupled to the cavity. Okay, this plays a role in the physics of the qubit cavity physics, but that we are not going to worry about it so much. But it does have an indirect effect in the quantity we are interested in looking at today as well. Okay, and again, as I said, the frequency of the qubit is usually lower than the frequency of the cavity. You can actually see that. Just put that here as well. Now, the reason, first of all, of course, the qubit and the cavity are connected because we are using the interaction between these two as a mechanism for making the measurement. And I think most of you, even I think Supriyo and Joydeep, you must have heard it at least in several talks, that the effective resonant frequency of this resonator depends on the state of the qubit. Of course, not this circuit, because this circuit is completely linear. This doesn't have that property, but that's the reason you're doing that. And then you probe the resonant frequency of this cavity, and from that you know whether the qubit is in the ground state or the excited state. But this cavity also plays another role. It's sort of a nice side effect of it. If you look at now how the qubit can dissipate its energy, which actually is a bad thing, because we actually don't want the qubit to dissipate its energy. We would like whatever excitation we put in the qubit to remain there forever. That would mean no decoherence at all, which in this language is completely basically saying that it is just the dissipation. Now, in reality, in a real experiment, it could be dominated by something to do with the inductor. Maybe the inductor has some losses or the capacitor has some losses. And so those will be like the internal dissipation, but we are ignoring that for now. And we are saying that the fact that this qubit has to be connected to the environment, and that is always needed because you have to bring signals in and out. And here in this case, you have connected it in this fashion. What is the amount of dissipation experienced by this particular circuit, this qubit? So remember that the right side is the qubit here, and the left one is the resonator. How much dissipation it is experiencing. So you do see that it is connected to the environment, but not directly, right? Directly would have been that if I had put a coupling capacitor here and then connected that to a 50 ohm port or something, then this would have set the one of the channels of dissipation, but there is no such thing in this circuit. So it is entirely going to dissipate only in this. This is the only dissipative element is the 50 ohm port, but it has to go through all of these things, right? So this is not a direct path for dissipating. And essentially all of this stuff protects the qubit from dissipating into this 50 ohm resistor. In exactly the same way as how this coupling capacitor allows you to decouple the environment from the cavity, Now there is a second coupling capacitor here, so this will also protect it. But then the most important one is actually this resonator itself, and the fact that the resonator's frequency and the qubit's frequency are not the same. So in the frequency space, there are two peaks, right? There is omega resonator and omega qubit, which is somewhat lower. Those numbers are, we just saw them. They are here, 5.63 and 7.21. Okay. So if you now think about this in the context of a filter, so imagine that this source of dissipation, okay, I guess usually we don't think about it of filters in terms of dissipation, but that is the purpose of this talk. But let's say that this is radiating some noise, Only the noise which is near the cavity frequency can actually transmit through the system. Remember, that's what that filter is. It's a band pass filter. On either side of that frequency, it actually attenuates the signal by reflecting it back into this. It's exactly the corollary of that the dissipation experienced by this guy is now a frequency dependent quantity and will have a maximum value close to the peak of the cavity frequency, and it will fall off because the cavity essentially suppresses the dissipation on this side. Okay. Now, sounds a little complicated, but have you guys understood what I'm trying to say, Jay?
Yeah, so we just saw that the transmission happens at specific frequencies, and in this LC case at one specific frequency. And as long as these two are different for the two LCs, most of the noise will be reflected back from the qubit.
Yes, but it is obvious in the case of when I'm talking about the noise entering from here, but here we are actually talking about something else, which is the dissipation experienced by this circuit, right? This is actually very intimately connected with that homework problem where I said that if I have a resistor and I have a capacitor, I want to make this into some resistor which looks like this and some reactance which is in parallel, just so that I can do some calculations, because I know how to compute a Q factor when the resistor is in parallel, right? This is exactly the same problem, except that this capacitor is now replaced by this more complicated object. So even though I gave the example because we were using the filter model, which usually talks about transmitting signals back and forth, there's actually a very deep connection. I mean, and all of you have studied this in a different context, which is called the fluctuation dissipation theorem, right? All of you have heard about the fluctuation dissipation theorem, right? Jay?
Yes, yes.
Shujita?
Yes. Yes.
Yeah, in which context have you heard about it?
In the context of these, any kind of scattering measurements, basically in response theory in quantum mechanics.
Yeah, so this is actually exactly the same. What it is saying is that the fluctuation coming from, so this is actually the fluctuations as discussed in the form of Johnson noise coming from the resistor is directly related to the dissipation it is able to put into that system, right? So in the context of the LC oscillator, this actually becomes very really stark and obvious to see. And there are some really nice calculations and things which I will cover maybe in a different, not as part of this course, but as a different discussion on this aspect of it. But it's basically the same idea that fluctuation and dissipation are inherently connected to each other. So that's why this model of considering which noise can enter from one side because of this filter is directly related to how much dissipation it experiences at that particular frequency. Of course, now there's an added flavor here that we have to think about what happens at each frequency band. Joydeep, is this familiar territory? Have you heard some of these ideas?
Yeah. So let's do.
Yeah?
Yeah.
Okay, and this connection which I made with the homework problem and what is happening here, this is also clear? This is just some other more complicated circuit which has a different kind of frequency dependence as opposed to the capacitor example. But essentially it's the same problem, and that's what we are going to just look at here.
Yes.
Okay. So the way to think about now is that from the point of view of this LC oscillator, the rest of the environment has some real part and some imaginary part. And the real part is what we are interested in, because that is the part which causes the energy to dissipate. And we would like to also look at it in this form as a parallel resistor to ground, because then I know how to simply connect. And then if there is a reactance part, that will cause some shift in the frequencies, right? Some small shift in the frequencies that of course will depend on the values of these various things. And because the frequency of the resonator is different, we know that the signal, because it's the same idea, right? You can think about, even in terms of signal propagation and dissipation, as the excitation present in this oscillator trying to go that way. And it cannot, because this circuit has a response which looks like this. And you are somewhere here at the lower end of the frequency. You could have been here as well, it doesn't matter, as long as you know how to compute that quantity, right? So that is really how this thing is. And for the qubit folks here, you might have heard this term floated around in some of our talks, the Purcell effect. This is what you're talking about, is that how is the environment, connection to the environment, modified by the presence of some other resonance circuit or something else in between, and how does one look at that? Because the only connection to the environment is via this network here. Okay, so what we need to do is, I said again, we want to look at something in this form. So we want to replace this whole thing with something, and stuff which is in parallel to ground is usually easily characterized by the Y admittance. Okay, so that's basically what we need to do, is we need to compute the real and imaginary part of the admittance as seen from outwards. Sorry, is there a question?
Yeah, one small question. So,
Yeah.
So if this readout cavity acts as a filter, let's say,
Yeah.
and then the actual signal which is getting to the going to the qubit, that will also getting attenuated, right?
Absolutely.
I mean,
absolutely.
So the going also the backward. So the reflected signal at port 1 will see 2 times attenuation. I mean, going backward.
Okay. So here's so this is now a detail regarding what is it actually used for. So remember again, there are two frequencies, omega qubit and omega resonator.
Yeah.
Okay. Now, and again, there are two types of operations one does with qubits. One is operations which change the state of the qubit. These are called, we call unitary operations. These are basically rotations of the qubit state. For that, the signal which is sent is at omega q. Okay. And you are absolutely right that this signal is going to experience some attenuation, which is going to be dependent on the exact nature of the filter function, because you are shining omega q is here, and whatever you send in here, it will not all reach there. But that's okay, because I can always increase the power of that signal to the level that I need to get to the qubit. Okay, these ideas we have discussed over and over again, even in other contexts, right? well, maybe not in this lecture, but Jay and Sujita the last two lectures of the general wiring, we had discussed this over and over again, that for the input side, it doesn't really matter. So we just increase the power and choose the correct amount of power that is required for that. But when we are doing measurement, which is when we are probing the state of the measurement, we send the signal at omega r. Now that omega r only sort of effectively travels only here. It does travel here, but it's sort of in some indirect sense. So that doesn't experience any additional attenuation or anything like that. So it's all because of the frequency separation of these two things. And in any case, we don't want the qubit mode to be coupled strongly to the outside world. In some experiments, in fact, in many architectures, for the convenience of some practical convenience, you separate the two ports. So the port on the left is actually used for the measurement. So this one is used for the measurement. And then they just put another very small capacitor here and then connect it to another port. Okay, this is now starting to look similar to the asymmetric design we had discussed earlier.
Yeah.
So even though you are introducing another channel for dissipation, but by keeping this very small, this capacitor very small, you can keep that dissipation small enough, and then correspondingly you have to put very large amplitude signal here as well. What's happening in this case is that that very small capacitor is actually being replaced by a filter, which is effectively giving you weak coupling. So they are both possibilities. But the point which you had raised is that the signal which is relevant for measurement, and that is actually the only signal we care about when we want to look at the signal which is coming back. So any signal coming back from the system is at omega r. And for the signals at the qubit frequency, you are actually not collecting any information. You just know that if you send a certain amplitude, the qubit will respond in a certain way. And the way you know that it has responded is actually by measuring the state of the qubit by looking at the signal at omega r.
Okay.
So of course, we are now getting into other kinds of details about the qubit, but that's the reason why this is okay. This point clear to everybody?
Yes.
Okay. So now all we need to do is to look at the admittance from this point here, with respect to the qubit. So let's see, since we have all defined as variables, I can make a duplicate here, which is identical. I will introduce now a port on this side, because I'm interested in the effective circuit here. And just to show you that it's the same, on the other side, I'm not going to put a port. I'm going to just put a resistor of 50 ohms. Okay, because that's what this is. From the perspective of this guy, this is just a 50 ohm resistor connected to ground. All right. So now we go to our graphs. So let's actually look at a new graph. Add measurement, and this is port 2, and the schematic is qubit resonators, and I choose port 2. In fact, I will choose this other measurement, which is linear and Y in. So admittance, input admittance. So remember that for single port, Y in and Y11 are the same thing, but this is now, and I'm going to look at real part, and I'm going to look at the imaginary part. Okay, and let's set up the range of frequencies now as 5 to 8. Okay, so there is the response, 5 gigahertz to 8 gigahertz. Let us just verify again the necessary frequencies here. So the qubit was at 5.63 and the resonator was at 7.21. Go back here. Let me put a marker on this at 5.63, somewhere around there. And here also, just change the axis so that this is. Okay. All right. Now, I'm going to change the y-axis to on the left side to log units so that you can actually see the full range. Yeah, there you go. Much better. In fact, it's very important to see it in log units because it really tells you the effect of the filtering. Okay. So first, let's look at the real part. All right. The real part of the admittance is peaking at close to the cavity resonant frequency, right? That makes sense because that is where the dissipation is maximum. So looking out from here, you expect that this thing is going to be coupled to the resistor most strongly when this circuit has the resonance, right? And we know that in parallel LC circuits, effectively the impedance of the LC circuit becomes infinite and it sort of drops out of the picture. But this value here, in fact, let's see what that value is 0.0059, all right? Now that is not equal to 1/50 because if it was 50 ohms, then Y is 1/Z. So it would have been 1/50, which is like basically 0.02. This is much smaller. And the reason for that is, of course, that there are also coupling capacitors, right? The coupling capacitors are also present here. So they provide a further decoupling from the 50 ohm environment. So this value here, this dissipation here is actually related to the bandwidth of the resonator itself, right? It's the dissipation at the resonant frequency of the cavity, of the readout cavity. So it's related to the effective impedance seen by that equivalent parallel LC circuit at that, the parallel RC circuit seen at that frequency, which is basically what you computed in the homework. And that's related to that. However, as you now move away from this frequency and you come close to the value around where the qubit is, that number has become extremely small. It's like 6.9 10 to the minus 7. And here this was something like 10 minus 3, right? 5.9 10 minus 3. So some 4 orders of magnitude have dropped. Right? That is telling you the effectiveness of the filter function. And why is this relevant? Because this here is this value, which is Y at omega Q. This is the real part of that. This is exactly related to the resistor here. So this R is 1 over that Y. Okay. So if this number is very small, then means that this R is very, very large. So this R is now, in mega ohms. And remember that for parallel LCR circuits, the larger the R, the smaller the dissipation or higher the Q factor. And that's really what we want to see here, is that the readouts LC circuit has suppressed the environmental dissipation to a very small value by making the Y very, very small, the real part of Y. The imaginary part of Y is out here. This is basically just the effective reactance which is coming from the rest of the circuit. And this will cause a shift in the resonant frequency of the qubit of this mode it won't be exactly at 5.63. It will be somewhere near it. So 5.63 is just the LC 1 over square root of LC number. But because of the presence of coupling capacitors and this, so remember that coupling capacitor just added simply in parallel, but here it's a little bit more complicated. The resonance, so you have to compute exactly what that number is, and that will shift the resonant frequency of the qubit slightly. And I can never remember this, but in the context of atomic physics, this is actually one of these things is also called the Lamb shift. It's the shift in the frequency of the atom because of its coupling to the environment through this. So there is a more deeper physics, which actually has a very simple microwave sort of engineering explanation of what is going on. Okay, so that's essentially what I wanted to show you, and how this affects this real part of the admittance, which is now relevant. And remember that this approximation, which I had also asked you to use in your homework problem, is only valid because the qubit resonator is by design supposed to be a very high Q oscillator, right? The internal losses of these things are supposed to be very small. Otherwise, it's not a good qubit. You don't want a very dissipative qubit. So that way, the coupling to the outside environment also has to be kept low. In fact, you should always be in a situation where you are not dominated by the coupling to the environment. Otherwise, you're doing a bad job of it. Because remember that you can always decouple and excite with a lot of power. So the excitation problem is not there. So whatever else, unknown physics or unknown material problem, which is setting the internal losses of this thing, that should ultimately set. Of course, there are experiments where you want the qubit to be decaying into the environment for other reasons, but most of the time you want the quality factor to be as high as possible. Since you cannot do anything to the internal losses, you try to make the external losses insignificant compared to the internal losses. Of course, in this diagram, there is no internal loss, but just to tell you, to make the comparison. So you want to be, to do two things. You want to keep the qubit away from the cavity resonance so that its coupling is weaker. And now you see that the point I was making about the rotating wave approximation and all, this is being computed from the exact microwave response of this particular circuit. Okay, let me get rid of these annotations here. If instead of the LC circuit here, I had used a transmission line, a λ/2 transmission line, that would have had a slightly different response, right? Remember, we compared the response of the λ/2 and the resonator. So even if they are identical, they might have, and you have matched the quality factor and everything, they might have similar responses, but only close to the resonant frequency. As you move away, and you saw that there was this asymmetry between the LC circuit and the transmission line version. And not just that, that even the LC circuit was not symmetric. What it means is that a point which is a certain distance away from the readout frequency on one side is not the same as on the other side. So in fact, let's plot this over a slightly larger range on the other side as well, so that we can see this slightly more clearly. You can see the same asymmetry showing up here. So we are at 7 gigahertz. This is about 5.6. So it's like 1.4 gigahertz this way. So if I go to 8.4 on the other side, this is much higher, almost 1 order of magnitude higher than this level. What this means is that equal distance away from the qubit on the higher and the lower side is not the same. The dissipation is higher on this side. And this is one of the reasons why at least many labs choose the qubit frequencies to be on the lower side, but it's not necessary. You can change this response by some other microwave engineering. However, when you use the rotating wave approximation, which only is valid for a small range of frequencies near the frequency, near the resonant frequency, that response actually is symmetric. that tells you that it should fall off symmetrically on both sides. Not only that, that also predicts a fall off which will match up to here, but then it actually will show that it's something like this. It shows a smaller fall off rate as opposed to the real LC circuit. So this is where it starts to fail, because the qubit by definition has to be at least several gigahertz away from the cavity. However, the rotating wave approximation only works for a few line widths, and the line widths of the cavity is usually much smaller. It's usually few megahertz. So that approximation is maybe valid up to tens of megahertz or 50 megahertz or 100 megahertz. But what you are interested in is the property about a gigahertz or two away. So that simple formula, which is called the Purcell T1, in fact, it has a very simple form, which is that T1 is 1 over kappa delta square over G square. Okay, so kappa is the line width of the readout cavity. So it's natural that you expect that the bandwidth of the cavity, which is basically related to the dissipation, is related to the T1 times, and T1 time is also just it's 1 over the damping of the qubit. Okay, it's just the inverse of that. And then it says that, and delta is basically the difference in the frequencies, and G is the coupling strength. So this G is related to the this capacitor in between. Okay, that's some overall scaling factor. So clearly, if the qubit and the cavity were more strongly coupled, this, in fact, we can see that if I tune this here. Oh, sorry.
What is kappa? Okay.
I'll tell you just 1 second. So just, where is this CRQ? There it is. So I just wanted you to look at the, let me get rid of this annotations again. Just look at the blue curve. It's also, freeze this. So if I increase the coupling capacitor between the qubit and the cavity, you see that this curve goes up, which means going up means larger Y and hence more dissipation, right? So this is expected because you're just now increasing the coupling to the outside environment, right? So that's just a point I wanted to make. And that is what is related to this so kappa is the line width of the cavity. I shouldn't, I'm just drawing this here as a reference that this is related to this resonance of the cavity. But it's basically just what we called gamma so far for all our resonators. In the qubit language, the line width of the readout cavity is usually given as kappa. And this is in radians unit, so there's a 2 pi factor there as well. And then delta is just the frequency difference, and then it goes as the square. So whether the frequency difference is positive or negative doesn't matter. This always gives you a symmetric result. And that in reality is not true, as you can see from this curve being asymmetric. And of course, depending on the detail of what exactly this resonator is, so what this object is, that frequency response could be very different. And if it's made of a transmission line, it will have multiple peaks, but usually that higher peaks are so far away that you don't care about it. And if it is a 3-dimensional cavity, it will have a different response. So this is sort of important to keep in mind in the context of qubit physics, that that Purcell formula, which is this formula I just wrote down, which allows you to calculate the lifetime of the qubit if it was limited by the dissipation imparted by the coupling to the environment via the readout cavity, only gives you correct results when you are very close to the resonant frequency, which unfortunately is not the regime in which you operate anyway, because you don't want to be very close to the resonant frequency, and hence this formula never works. It only gives you a rough estimate of where it is. Almost always the real dissipation is smaller, so it's sort of a nice thing that in practice, the real dissipation, the formula actually overestimates the dissipation, and the real dissipation is actually smaller because the function falls off a lot faster than what is predicted by the single mode rotating wave approximation one can use to compute, because that simple formula only comes from that approximation. Otherwise, it will be a lot more complicated. And then, the fact that higher frequency and lower frequency are different, and also the fact that when you have a transmission line resonator, the asymmetry itself is quite different. So when you have higher modes, it actually makes the dissipation to the right of the first mode somewhat worse than what you would get for a single mode, which is just a single LC oscillator. Okay, so these are details, but just from the context of the microwave concept here and the thing, this is basically what I wanted to show you. So the calculation which you did for your homework problem was just the very simple case of just computing this. And not just that, it was the simple case of computing this at one frequency, which is the frequency at which you are computing the result. So because at any one frequency, you can, a series and a parallel can be interchanged with each other. So that was the approximation you had to make. So this would give you some real part of the admittance and an imaginary part of the admittance. The real part of the admittance will become the resistor. The imaginary part of the admittance will become the effective additional capacitance. And what you will find is that the imaginary part of the admittance is the same as the value of the capacitor itself. So you can just replace the capacitor part, and then you can actually compute an expression for what this Y is, or 1 over R, which is basically what you are doing it, in terms of the capacitance value and the frequency, and then it basically allows you to make a guess. And once you have that, you can compute the Q factor. Okay, so yeah, so that's a good place to stop. I will send you the reading material for looking at other kinds of filters in more detail, and then we will discuss that maybe in a couple of lectures after I finish the scattering theory part of the macros. Okay, any questions?
I think I completely misunderstood the assignment question. Can you just maybe explain it once more?
I mean, you must misunderstood this explanation or the original question?
So let's say let us just consider an LC oscillator coupled with a biocapacitance to some port. What equivalent?
Okay, so the problem you had is basically this, right? The port is also not relevant. It's just a 50 ohm resistor to ground is what is relevant. Okay. And it is coupled by some capacitor CC. Now, what are the things we already know? We know that if I have a simple LCR circuit like this, LCR, I know how to write down Q. That is the formula. Okay, where omega 0 is 1 over square of LC. Okay. So the first point was, if I have something like this, can I write it in this form so that I can apply my knowledge of this formula to compute the Q factor? The whole thing is about computing Q factor, right? Or the line width or the bandwidth. So what I had said is that what I actually have is this, have 50 ohms and coupling capacitor. But I want this to look like a parallel R to ground in parallel with something else, which I had already even sort of given you the answer that it is actually just a capacitor. So the only thing you had to do was to equate the response of these two circuits, and because these responses are frequency dependent, now you have to make a choice of the frequency. And what is that frequency? That frequency is this frequency, because that is the only frequency you care about, because you want to know what is the dissipation presented by this circuit at the resonant frequency of the qubit. But of course, omega naught also gets shifted because of this additional capacitor. And by equating the two, you basically now can get an expression for what this R prime is in terms of R and Cc. And what I showed you today was exactly what that response function is looking at. Just basically computing the real and imaginary parts of that at one frequency, and then coming up with an effective model, which again, remember, it is only valid at that frequency. It will not satisfy the frequency dependence of the true problem. But the reason it's okay to do that is because out here, sorry, maybe this is not the correct way to do it. Let's see. Okay. The reason, even for the qubit case here, the reason we can do this is because near the qubit frequency, the response of the resonator's function, this blue curve is basically related to the resonator and the coupling capacitors. It doesn't have any sharp feature like this. It's basically a smoothly varying function, and it's smoothly varying very slowly on the range of frequencies where the qubit's own resonance is changing. So qubit frequency is out here, but it's a very sharp response. So the other thing is more or less constant. Whereas in this problem, this part of the circuit doesn't have any resonance at all. It's just a smoothly varying function. And then the relevant frequency is the frequency of the actual resonance circuit, which is the LC circuit. So we just pick the value. So it's just an approximate way of computing what the effect of the dissipation is. And so that you can see, what is the functional dependence on C of C? What is the functional dependence on R? If I double the R, will the Q become double, or it will become half if I double the value of CC? So this was just an exercise to get a sense for what that function form looks like. But in essence, what I showed you today is what is going on there, like why you can actually do that. Is that clear?
Yeah, makes sense.
So you're doing two approximations. One, you're assuming it's a smooth function, and the second, that is actually not only a smooth, it's a constant at that particular frequency. So at each frequency, you can always do that. You can construct any circuit you like, because the only thing which gives any reality to the circuit is whether the values of the properties like impedance, admittance, or reflection coefficient is matching. That is one number. And is it matching over a wide range of frequencies? So if you restrict and saying that I only care about one exact value of frequency, which is the approximation we are making, then you can build any circuit you like. You just need a real part and an imaginary part. That's all, right? You have a real part of the admittance and a real part of the imaginary part of the admittance. Then you can construct it in any circuit. We chose this circuit because we know how to compute the quantity we are interested in for this particular circuit. I mean, there is no guarantee that, remember that if you only have, so X, which is the reactance, is, in fact, let's say that Jx is the reactance. This, if it is an inductor, would be, X will be omega L. And if it is a capacitance, it will be minus 1 over omega C. And depending on how you do it, you can absorb the minus, and the whole thing can be sign independent as well. So whether one has to include a capacitance or an inductance, one has to see. And then from the sign of that, you can say, okay, this, if I have a parallel capacitance, it still gives me the correct sign for the reactance, so it's okay. And in this particular case, with that approximation, the parallel capacitance turn out to be having the same value as this one. And I think that I had already given in the problem. I don't remember now. Did I give that in the problem, that these two capacitances are the same as an approximation? Shajita, did I give that approximation? Or
No.
anyway, okay. But were you able to derive it, that it should be the same? I haven't looked at your
I-
solutions yet, but maybe I'll check what you and Joydeep have submitted and then maybe show you exactly how to do it. I mean, this is not such a big deal. This was just mostly to get you used to looking at these kind of quantities. But from the point of view of the physics or the microwave engineering, that's what we are actually doing. And that is even more apparent in this example, which we looked at today, that the qubit's local environment is set by the cavity's response function, but only at a very narrow frequency near the qubit's frequency. And that's how one would come. Okay, any other questions? All right, okay, not stop there, and we will then meet on Tuesday, the Thursday at 5. And I'll send you some reading material for the scattering matrix part as well. And please do read it. Okay, all right. See you on Thursday.